See, today I am going to talk about linear discriminant analysis. And to begin with, I am going to demonstrate you the possible cases through graph. As we know that when we deal with a data, we have instances and features. Now, linear discriminant analysis is applicable when you have features in numeric form. Categorical is not applicable. So if you have features with numerical values, real values, then linear discriminant analysis is very well useful. For example, in iris data, sepal length, numeric, sepal width, numeric, petal length, numeric, petal width, numeric. In such cases, linear discriminant analysis is applicable. Now, this linear discriminant analysis is based on a probabilistic approach. It is based on density. See, Bayesian is based on probability where you need not require the probability distribution as such. In case of linear discriminant analysis, you need a distribution of your features. That is very important. And so, try to understand the difference between support vector machine, logistic regression, Bayesian classification, and linear discriminant analysis, and KNN, that is we will see later on. So there are two things to remember. In linear discriminant analysis, you need to have a data in a numeric form. And number two, you need the distribution as such. So I will show you few graphs, and by that way, we will try to understand what is it. Okay, can you see my screen? Is my screen visible to you? Yes, I hope my screen is quite visible to you. Okay. Let us see these two graphs. The red one is f of x equal to 1 upon root 2 pi e to the power minus half x square. So this is your standard normal with mean 0 and variance 1. Let us take green graph. 1 upon square root of 2 pi exponential of minus 1 by 2 x minus 7 bracket square. Let us see these two graphs. Now these two graphs means what? Reddish one corresponds to feature 1. Reddish 2 corresponds to feature 2. Okay. Or you can say reddish 1 corresponds to data 1. Reddish 2 corresponds to data 2. So suppose reddish 1 corresponds to iris setosa. Greenish correspond to iris versicolor. So category wise, these two data sets are shown by two different colors. Now let us try to read these two graphs and try to understand the similarity and dissimilarity in these two categories. The first category similarity we can say is these two graphs have same distribution, that is both are normal. This is one similarity. Second similarity is both have same variance. Second similarity. If you talk about the distinction, you will see that the first one have mean 0 and second one have mean 7. That is the distinction. Now, what is the effect of this distinction? What is the effect of this distinction? You can see The effect of this distinction is that the two curves, two graphs, two densities are quite distinct from each other. Quite distinct from each other. It means what? An observation belonging to reddish one is very rare to classify in greenish one. That is the meaning. The observation belonging to reddish one is very rare, very, very rare, that is classified in greenish one. And vice versa. An observation from greenish data set is very rare to be classified in reddish one. That is the effect of dissimilarity. That is the effect of two distributions having two different means. And so, in such a situation, the problem of classification is not at all serious. Not at all serious.
Not at all.
Because the probability of misclassification is very rare. As I told you, that the classifying the data from reddish distribution in greenish one is very rare. That means it's a misclassification. Classifying an observation from greenish one to reddish one is again very rare. That is again misclassification. So probabilities of misclassifications are very rare. That means you have a very high chance, high degree that an observation from reddish data can be classified in reddish itself with a very high probability. Again, with a very high probability, an observation from greenish one will be classified in greenish itself with a high probability. And so, problem of misclassification is very rare. And so, the problem of classification, problem of separation is very rare in this case. That is what we can predict, we can understand by these two graphs. Now we'll go to the one more. Let us see these two graphs now. Let us see these two graphs. Here also you have some similarity, here also you have some dissimilarity. Talking in terms of similarity, you can say that both are normal in nature. Both have same variance, but their means are different. One has a mean 0, another has a mean 2. Now, what is the effect of a slight distinction? See, in earlier case, the distinction is quite clear, quite clear. But here, you can see there is not clear-cut distinction. There is a kind of a overlap. There is a kind of a overlap. Now, if you see, if your observation is below this -1, below -1, then it is with high probability it will belong to reddish data. If the data point is below -1, with a high probability it will belong to reddish one. If your data point is greater than 5, greater than 4, greater than 3, with a high probability it will belong to greenish data set. But if you come here, for example, Okay. If you see, if you are here, if you are here, yes. Okay. See this. Right. Okay. See here. If you are in between this or in between this, you will find that there is a chance that a data from reddish can be misclassified to greenish one. And at the same time, data from greenish may be classified to reddish one. That's the possibility because it's overlapping. And because of overlapping, the problem of probabilities of misclassification becomes serious. So there are high probabilities of probability of misclassification. And so in this case, problem of classification is serious one because of overlapping. You need a separation, and that separation should be such that the probability of misclassification should be as minimum as it is possible. And so this is the problem here. Now we'll go to some another one also to understand this. Okay, let us see this. Another one. Again, talking in terms of similarity, you can say that both have normal distributions. But now there are two dissimilarities. Their means are different. Their variances are also different. Their variances are also different. And therefore, you will see that the reddish one is quite spread over, whereas greenish one is quite compact. Quite compact. See, if I change the variance, you will see the compactness of greenish data. It becomes more narrower, whereas the reddish one is flatter one. Flatter one, right? See this. Another one. Variance is more. And so the distribution becomes quite flatter enough. Quite flatter enough. And that will change the probabilities of misclassification. That will give an impact on probability of misclassification. Because if you talk about the line, okay, see here. See here. You have a more serious problem when you are from x is from minus 1.3 to 1.7. When you have x minus 1.3 to 1.7. So here you have more serious problem of probabilities of misclassification. Even you can go beyond this also. You can think of this also. You can think of this also, right? Even here also you can think of this. So see, the probabilities of misclassification is becoming very high because your mean and variances are different, and that mean and variances are different, that gives a different shape for overlapping area, and that overlapping area will be very important for understanding the probability of misclassification. Okay, now I will talk about this. See this. See this. Here also you can see that both the distributions are normal in nature. Their means are same, but their variances are different. And therefore, there is a still problem of classification. And in this case, problem of classification is really very serious. Really very serious. See this. See, the problem of misclassification is changing. Problem of classification is becoming serious. See here, right? Okay. Now we'll go for some other distribution. I will explain you some other distribution now. Right. I think you might have understood the distribution which I have given. See the dissimilarity. One distribution is normal, another distribution is Cauchy, and if you see their overlap, yes, there is overlap, and that overlap will cause the probability of misclassification. So if your one feature, if your one data set belongs to normal, another data set belongs to Cauchy, you have this type of situation. For example, if you go here, even then also there is a problem of misclassification. If you go here, there is also problem of misclassification. If you go here, the problem of misclassification is not that much serious because the center, you can say, one has a center at 0, other has a center at 15, quite distinct from each other. So when you have this, then definitely there is a problem of misclassification. And so we have a question of how to define a rule, that is linear discriminant analysis, by which it is quite possible to make a distinction between two data sets. Now I will explain you graphically how it's quite possible, and in the next lecture we will go for its mathematical derivation as such. Let us see this. Let us see this. These two distributions, as we know that they have same form, normal, same variance, 1. The distinction is between what is called as mean. Now let me put a line here, say x equal to 1. Suppose I have dropped a line x equal to 1. Now if you see this x equal to 1, this line is passing through. This line is passing through. Can you recall where from it passes? Can you recall where from it passes? See, this point is the point of intersection of two curves. And you see that your line x equal to 1 passes through this point of intersection. Now, suppose I have a point here, means between 0 to 1, suppose I have a point. Now, if I have a point between 0 to 1, suppose this point, say 0.5. If I come here and if I come here, you will see that reddish curve give me more likelihood at x equal to 0.5 and greenish curve will give me less likelihood at x equal to 0.5. What it means is that x equal to 0.5 is more likely to belong to reddish data set, reddish curve, reddish category, whereas it is less likely to belong to greenish one. That is the interpretation we can give through graph. If we come to say this 1.5, this point will give me the likelihood of normal 0, 1 at x equal to 1.5, and this will give me the likelihood of x equal to 1.5 for normal 0, normal 2, 1. So you can see the role is changed. And the point 1.5 will belongs to with high probability in greenish data set, and it has a very less chance to belongs to reddish data set. So this is quite possible because we have a lot of similarities, and because of this similarity we got this point of intersection and this line. This is called as linear discriminant analysis. We can derive this, but I have just shown you by graph. And so what is your rule? If your observation x is less than 1, it will belong to reddish one. If your observation x is greater than 1, it will belong to greenish one. If your observation x is equal to 1, it is not possible, because in case of continuous distribution, probability at a point is 0. And therefore, this is the rule. But when you have a lot of dissimilarity, describing such a rule needs a lot of mathematical treatment. Another thing we have to think of is we have to attach with this prior probability. What is the chance that it may belongs to greenish one? What history says, according to historical information, what is the chance that it will belong to reddish data set and it will belong to greenish data set? So that prior probability we have to attach, if possible, we have. In case of equal prior probability, we are here at x equal to 1. But if your prior probabilities are different, then your rule will also change. Another thing is we have to attach is there any cost of misclassification? What is the cost of misclassification of classifying an observation from reddish data to greenish one? What is the cost of misclassification of classifying greenish data to reddish data? So this cost we have to attach. So if you make our problem more complex by adding prior probabilities and by adding cost of misclassification, the defining, the describing, the forming, the rule of misclassification needs more mathematical treatment. So this is the simplest case. This, whatever the present case I am showing you, this is the simplest case. And in this case, it is very simple to derive the rule. And that rule is, if x less than 1, it will belong to reddish one. If x greater than 1, it will belong to greenish one. That is very simple one. So we have to take care of prior priorities. We have to take care of cost of misclassification. So have you understood up to this by means of graph? So in tomorrow's lecture, I will try to give you the mathematical treatment of this. Okay. Have you understood this by graph? Yes. Please put in chat box. Have you understood this by graphs? Different possibilities. Different possibilities. No. Very good. No. Okay.